Have you ever looked up at the night sky and just felt, completely overwhelmed by how complex it all seems, and maybe wished there was a way to really get it, from the tiniest particles to, well, galaxies, without needing a ton of advanced math? If that sounds like you, then you are definitely in the right place today. We're doing a deep dive into this really fascinating source from back in 1960. It's called Atoms, Galaxies, and Understanding by a Dr. Daniel W. Fry. And we're doing this dive specifically for you to cut through that complexity. Fry's whole goal with this book, his mission, was basically to help the everyday person, the beginner, understand cosmology. And he did it by swapping out the heavy math for, as he put it, simple discussion, explanation, and analogy. Now, here's the really bold part. He claims this approach can help us predict physical laws, even if we've never formally learned them. It's about building this intuitive feel for how the universe works.
Yeah.
That's quite a promise.
It really is. And Fry was smart about it. He knew math is universal, sure, but it's also a language you have to, learn first. His approach was different. Make it accessible. Build understanding conceptually from the ground up, not just plugging numbers into formulas.
Right. And he starts right at the beginning. I mean, really the beginning. The whole first chapter is just definitions.
Yeah.
Honestly, when I first saw that, I thought, definitions, really? But he makes a really strong case for why it's so crucial.
Yeah.
Especially in cosmology, where words can be fuzzy, and that leads to a lot of confusion down the line.
Exactly. And it's not just any definitions. He's incredibly precise. It forces you, the reader, or listener in this case, to think critically right away. You have to make sure your mental picture matches his. Take reference point. He hammers home immediately that it's never absolute, always relative. The example he uses. A person sitting still on Earth. They're also zooming through space relative to the moon or the sun. Instantly sets the stage. Everything depends on your viewpoint.
Yeah, that simple idea changes everything. You can't just say it's moving. It has to be moving relative to what? Always specific. Motion, velocity, always tied to a reference point. Seems basic, but it shifts your whole framework.
It does. And then there's energy. He doesn't just leave it vague. It's specifically the ability to create changes. And here's the clever bit. It only really exists or acts when there's a differential he calls it, or when it's split into poles, positive and negative charges. Think of like water only flowing downhill because there's a height difference. Same idea. When these poles are united, balanced, they form a photon, a quantum of energy.
Okay, so divided energy leads to
Fields.
Right. Areas of influence, electric, magnetic, gravitational. They're just what happens when energy is divided. And finally, mass. Not just stuff, but resistance to acceleration. And crucially, he ties it to both matter and energy. That's key later on. So what's the payoff for all this groundwork? It means we're essentially learning the universe's own language right from the start, building that solid vocabulary so when you talk about atoms and galaxies, we're all hopefully on the same page.
And that clarity is vital before we jump into the really tiny stuff that makes up everything, the actual building blocks.
Speaking of tiny, Fry introduces the big four, or rather the incredibly small four, the neutron, proton, electron, and photon. And the first thing he points out is kind of mind-blowing. No man has ever seen any of the four. They're just unimaginably small. We infer them, we measure their effects, but we don't see them directly. Yet the first three make up all matter, and the fourth, the photon, drives all change.
Yeah, it's humbling. And to help us wrap our heads around these unseen players, he comes up with this brilliant conceptual tool. He calls it the nullitron. Now, this isn't a real particle anyone's found. It's a thought experiment. Imagine something that only has inertia, just resistance to being pushed or pulled. No charge, no energy, no field, just pure inertia, like a perfectly featureless speck doing nothing.
It's a great starting point. Then he says, okay, take that nullitron and add a quantum of energy, a photon, so it's fully contained within it. Boom, you've just created a neutron. Now it has inertial mass and gravitational mass. Its positive and negative charges are united inside, so no external electric field, but it does have a gravitational field.
Right. And then the next step, if you can somehow divide that internal energy, pull the negative charge out from the core so it forms a kind of shell of force around the positive core. Well, now we've got the simplest atom, hydrogen. The core, the former neutron center, is now a proton. Positively charged, holds most of the mass, still has gravity. And that shell of negative force, that's the electron.
Okay, now this part really messes with the standard picture, the textbook atom. Fry basically says that image of a tiny electron zipping around the proton like a planet is.
Right.
Well, not quite right. He describes the electron as extended or stretched out along the path of its orbit until it becomes a ring of charge occupying simultaneously all parts of its orbit. Whoa! And then if you rotate that ring, it creates a sphere of charge around the proton. So think less tiny dot, more shimmering sphere of influence.
It's a really different way to visualize it, isn't it? It helps explain atomic behavior, especially field interactions, much better than the simple orbital model. And from that basic hydrogen atom, he starts building, add one neutron to regular hydrogen, 1H1. You get deuterium, 1H2, heavy hydrogen.
Okay.
Add another neutron, you get tritium, 1H3, heavy, heavy hydrogen. But chemically, they're all still hydrogen.
Right, because isotopes, yeah. He makes the point that chemical properties are determined by the number of electrons in the shell and the number of protons in the core. Adding neutrons just makes it heavier.
Exactly. But keep adding neutrons, and eventually, the atom gets unstable. The internal forces can't hold another one without that neutron's energy dividing. So the neutron ejects its negative charge that becomes a new electron joining the outer shell. And what's left of the neutron becomes a new proton in the core.
Ah, so that's how you get the next element up, like tritium becoming helium, 2He4. That makes sense.
Yeah, though he does mention some elements, like lithium, seem to need two neutrons added at once, which is tricky.
And he notes that while we can't just keep forcing neutrons in one by one easily with current tech, some transmutations are possible, like making plutonium from uranium-238 by adding neutrons.
Right. Then he zooms out a bit, defines a molecule. Smallest particle of a compound, atoms linking up by expanding their electron shells to enclose each other, like H2O, water.
And he revisits the old Greek idea of the atom meaning indivisible.
Which, of course, we now know isn't true. The atom's not indivisible at all. It's this intricate, complex mechanism.
And here's another stunner from the book. The atom is practically all space. Like, the actual particles take up maybe 1 million trillionth of the volume. It's staggering.
It really is. So what makes things feel solid? He says it's the powerful fields operating within all that empty space.
That really does raise the question, doesn't it? If it's mostly empty space, why does my desk feel solid?
It's a fantastic illustration of how these invisible fields literally shape our reality. Makes you rethink what solid even means at that level.
Okay, so we've got our atoms built from these fundamental bits, mostly empty space held together by fields. Now, what happens when they interact? Fry asks us to picture two simple hydrogen atoms just floating out there in space.
Okay, so you've got two forces at play. The electron shells, being negative, repel each other electrically, pushing them apart. But the protons in their cores have mass, so they attract each other gravitationally, pulling them together.
And Newton's inverse square law applies to both.
Yep, but the distances are different. Electrical repulsion acts between the nearest points of the shells. Gravity acts between the protons deep inside. So there's this sweet spot, a critical distance, where the attraction exactly balances the repulsion.
But they don't just stop there, do they?
No, because as they fall towards each other, they gain momentum. So they overshoot that balance point, get too close, repel, bounce back, overshoot again. And since he describes atoms as perfectly elastic in this ideal scenario with no friction, they just keep oscillating back and forth indefinitely, always seeking that balance, always carried past it by momentum.
Fascinating, like a constant dance.
And something that constantly affects that dance, that critical distance, is the photon, the particle of energy. Its energy level depends on its frequency, remember. Within that whole electromagnetic spectrum, radio waves, visible light, X-rays, all that Fry focuses on infrared photons, heat energy. He says these are readily absorbed by the electron shell.
And when they absorb that energy?
The shells expand. They occupy a larger volume.
Okay, hold on. If infrared is heat and absorbing it makes electron shells expand, then you could actually predict. Wow, you could predict that heating something makes it expand. Not because you memorized a rule, but because you understand the mechanism at the atomic level. That's what Fry means by predicting physics.
Exactly. You derive the rule. The addition of heat energy will tend to cause that matter to occupy a larger volume. The loss of heat energy will tend to cause that matter to occupy less space or to contract. It flows logically from the model.
That is genuinely powerful, that feeling of understanding why, not just what.
And this expansion idea also relates to escape velocity. If an atom suddenly absorbs a lot of photons at once, it expands rapidly, accelerates hard, and might actually achieve escape velocity from its neighbors, flies off on its own, like a tiny rocket.
So when you go from just 2 atoms to like billions and billions.
Then you start seeing the statistical effects. Most physical laws, he argues, are the statistical result of countless tiny individual actions. He uses a billiard ball analogy. Think of photons as tiny random Q strokes hitting the atoms, balls. You can't track every single hit, but you can talk about the average motion, the overall temperature.
Which leads nicely into defining temperature. It's the measure of the rate of motion of its particles. Faster motion, more collisions, higher temperature.
Right, and absolute zero is that theoretical point where all motion stops, which is practically impossible because the atoms would have to lose every single photon they could possibly emit.
He also distinguishes between two types of heat.
Yeah, active heat, which is the kinetic energy, the actual motion of the particles, and latent heat, which is the energy stored within the electron shells as photons. Specific heat, then, is just the ratio between the two. Water is 1.000, the standard.
And you can increase temperature not just with photons, but with work, right? Like a blacksmith hitting an anvil.
Exactly. Work by impact. Or rubbing your hands together, work by friction. Both convert large-scale motion into that random jiggling motion of particles, increasing the active heat.
Okay, this is all building a really solid picture.
Yeah.
So the states of matter: solid, liquid, gas. How does this model explain them?
Solids. Low photon content, shells are small, particles are kind of locked in position relative to each other, holds its shape.
Makes sense.
Gases.
Yeah.
High photon content, shells are large, particles have reached escape velocity from each other. They just expand out indefinitely, bouncing around randomly. You talk about their mean free path, how far they go between collisions.
Okay, solid gas, standard stuff. What about liquid?
Now here's where Fry throws a curveball. He says liquid is not, in the strictest sense of the word, a true state of matter at all.
Wait, what? How can liquid not be a state of matter?
His argument is that it's entirely dependent on outside forces, like gravity holding it down or atmospheric pressure pushing on it. Take away gravity and pressure, he says, and a liquid would either act like a soft solid, maybe pulling itself into a sphere due to surface tension, or more likely, it would just behave like a gas and dissipate.
He gives an example, right? About water boiling.
Yeah, a great one. Water in a vacuum chamber can boil vigorously at just 100 degrees Fahrenheit, which is barely lukewarm. Shows its tendency to become a gas when that external pressure is removed.
So next time I pour a glass of water, I'm basically looking at a very constrained gas. That's wild.
It's definitely a provocative way to think about it.
Okay, so from states of matter to how heat moves between them. Conduction, convection, radiation.
Right. Conduction is particle-to-particle transfer, mostly in solids, like heat moving down a metal rod. Convection is heat carried by the movement of the fluid itself, hot air rising, boiling water circulating. And radiation is just energy traveling as photons, like heat from the sun or a campfire.
He uses the torch on an iron bar example to show all three at once.
Perfect example. The torch flame itself radiates photons onto the iron, radiation. The hot gases from the torch physically flow onto the bar, convection. And then the heat travels through the solid iron bar itself, conduction.
And you see the bar get red hot, then white hot.
Exactly. As the temperature climbs, the frequency of the photons being emitted by the iron atoms increases, shifting the color we see. Eventually, if you keep heating it, the particles gain enough energy to reach escape velocity from their fixed positions. It melts.
What about compressing a gas, like in a piston?
If you push the piston in, you force the gas particles into a smaller volume. They don't necessarily gain more total photon energy instantly, but the energy density goes up. They collide more often, more violently. The temperature rises because you're concentrating the kinetic energy. He calls it squeezing heat out. And that principle, compressing a gas to heat it, letting it expand to cool it, that's the core of how most refrigerators work.
Amazing how these fundamental ideas connect to everyday tech. And this leads to pressure.
Yep.
Pressure is just the collective force of all those gas particles constantly slamming into the walls of their container or any surface.
Depends on how many particles there are, how fast they're moving, and how much mass each one has.
Right. And it's directly linked to temperature. Temperature measures the total kinetic energy in a volume. Pressure measures the force that energy exerts over an area.
He gives some mind-boggling numbers for air pressure at sea level.
Oh, yeah. Something like 400 quintillion particles per cubic inch, moving at an average of 1,760 feet per second, each one colliding over 5 billion times per second. All that tiny, frantic activity adds up to the 14.7 pounds per square inch we feel constantly. It's incredible.
It really puts everyday reality in a different light. All that invisible chaos holding the atmosphere up.
And connecting these micro actions to macro forces we experience, that's the bridge Fry builds so well. Okay, so we've built atoms, seen how they interact, how heat works, states of matter, pressure, all based on these fundamental principles. But now Fry really starts to shake things up. He challenges some core assumptions about physical laws themselves, nonlinearity.
This is where it gets really profound. He talks about how our fixed ideas about gravity, space, time, energy, thinking they were absolute, unchanging, actually held back progress, like achieving space travel.
Until Einstein came along in 1905 with special relativity, showing they were all variable, interconnected.
Right. But Fry argues that many scientists kind of missed the deeper point. They focused on the math, the formulas, but maybe didn't fully absorb Einstein's philosophical preface. This created, in Fry's words, thought blocks.
And his solution, or his alternative view, is this idea of the great curve of natural law. He says physical laws aren't straight lines within their own domains. They're actually segments of one single, vast, underlying curve.
The surveyor analogy is perfect. For a small field, you can treat the ground as flat, but map a whole continent. You absolutely have to account for the Earth's curvature. He's saying physical laws are like that.
So instead of thinking about, say, linear laws operating in a curved space, which is hard to visualize,
Yeah, very abstract.
he suggests thinking about the laws themselves as being curved, like a sine wave. Sometimes they're positive, above the zero line, sometimes negative, below it. That, he says, you can picture and work with conceptually.
And this view, again, hammers home the relativity point. None of the basic factors have any reality or significance except when considered from a specified position or condition. Where you are on that curve matters.
Okay, apply this curved law idea to gravity. Newton gave us the inverse square law. Attraction proportional to mass, decreasing with distance squared. Works brilliantly, mostly.
Mostly. But Fry points out the zero distance problem. If distance is zero, the formula gives infinite force. That doesn't make sense, especially inside an atom. How do you define the distance between particles? It gets messy.
And here's the kicker. He says that intense binding energy, holding protons and neutrons together in a nucleus. Under the right conditions, the gravitational force component of it can actually become negative, repulsive.
He uses uranium-235 fission as the prime example. Add just one slow neutron, and suddenly the gravitational force within that nucleus flips, becomes negative. Repulsion takes over, and the nucleus splits apart, fission.
And the key is that it's low-speed neutrons that do this, not high-speed ones smashing into it. It's about the presence of the neutron, changing the conditions within the nucleus, pushing that gravitational force onto the negative part of its curve.
It's totally counterintuitive if you only think of gravity as attraction. It suggests gravity, like other fields, might have a dual polarity.
He mentions that old idea of levity.
Yeah, the discredited theory that some things naturally repel gravitationally. He says they misapplied it, thinking hydrogen floated because it had levity. But the basic idea that a fundamental force could have both attractive and repulsive aspects, that philosophical core was actually right, just overlooked for gravity.
Mind blown. Okay, so if gravity can be negative in the microcosm, what about the macrocosm, the universe?
This is where it gets really elegant, the big cosmological puzzle. If gravity is always attractive, why is the universe expanding? Why are galaxies flying apart instead of clumping together?
The Big Bang theory is the standard answer, but Fry points out issues there too. If Newtonian gravity was the only force at play right after the bang, wouldn't it have been too strong? Wouldn't everything have just collapsed back immediately?
His nonlinear gravity offers a different solution. Within a galaxy, where distances are relatively small, gravity follows the normal attractive part of the curve, holding stars and planets together. But in the vast spaces between the galaxies, he argues, the curve dips below the zero line, with the result that a repulsion exists between the galaxies themselves.
So attraction within galaxies, repulsion between them, all part of the same curved law.
Exactly. He even mentions some scientific papers from the late 50s by Noon, Spencer, and Zwicky that were apparently pointing towards this very idea: positive gravity locally, negative gravity cosmologically.
Okay, if this is true, the implications for space travel are huge. We've been thinking about it all wrong.
That's his point. We've tried to destroy gravity, failed, shield it, failed, or just brute force overcome it with rockets.
Which he calls incredibly wasteful, like trying to push a rowboat by throwing rocks out the back.
Yeah, rockets are limited by how much fuel you can carry, how much energy you can release, and crucially, the strength of the rocket chamber itself, the mechanical strength of the throwing arm. Even nuclear power faces huge engineering hurdles for propulsion.
So instead of fighting gravity,
He asks, isn't it about time we began to consider the possibilities of making use of it.
Use the negative part of the curve.
Precisely. If you could arrange the conditions around a spacecraft, maybe manipulating electrical charges or fields in a specific way to place it in that negative portion of the gravitational curve relative to Earth, then it would just fall away from the Earth as easily and as naturally as a stone drop from a tower falls toward the Earth. No brute force required.
But people would say negative gravity is only in atoms or between galaxies.
And Fry anticipates that. He reiterates, laws are relative. The shape of that curve isn't fixed. It's modified by the mass present, but also by the number and position of the electrical charges. You might be able to manipulate the local curve.
He uses that magnet analogy, right?
Perfect analogy. A magnet and an iron bar normally attract. But wrap the iron bar in wire, run a current, create an opposing magnetic field, now they can repel. You didn't destroy the magnetic field, you polarized it. You changed the local conditions.
Maybe we can do the same with gravity.
That's the hope he offers. It should not be too difficult to work out means of polarizing a gravitational field once we discard the old assumption that it is impossible. Stop fighting it. Start manipulating it.
That is a fundamentally different way to think about propulsion in space travel.
Wow. It really opens things up, and it flows naturally from understanding these deeper concepts about mass, energy, and relativity that he lays out.
Right, let's touch on mass and matter again. He's
Yep.
very clear. Mass is resistance to change in the existing state of motion.
And he splits it: inertial mass, general resistance, and Newtonian mass, the kind matter has that follows Newton's laws.
Why does an electron have mass then?
Because it has an electric charge. When you try to accelerate it, you have to create a magnetic field around its path, and that takes energy, which manifests as resistance to the acceleration, hence mass.
Okay, what about that whole infinite mass at the speed of light thing? We hear that all the time.
Yes. Fry tackles that head on. He says it's a common misunderstanding. That infinite mass an electron supposedly gets at velocity c isn't inherent. It's only infinite in reference to its original energy level. It's really just a measure of the kinetic energy differential between the observer and the point which he is observing. It's relative.
He has that corkball analogy to explain this.
Yeah, it's a good one. Imagine you're floating in space, shooting 10-gram bullets at a 10-gram cork ball. The first bullet adds a lot of speed. The second adds less, because the relative speed difference is smaller. The third adds even less. From your perspective, it looks like the cork ball is getting heavier, harder to accelerate. Its apparent mass increases. If you could somehow get it near light speed relative to you, it would seem infinitely massive to you.
But if you then hopped in a spaceship and matched the corkball's speed,
Poof! Relative to you, its velocity is now zero. Its infinite mass completely vanishes. It's back to being just a 10-gram cork ball. It was all about the energy difference between you and it.
so mass isn't absolute. It depends on the observer's energy state relative to the object. That's huge.
It's fundamental to relativity. Which brings us back to Einstein and that preface Fry emphasizes.
The one that gets left out.
Often, yeah. Einstein basically said, trust your senses for your frame of reference. What our senses tell us is true. If you observe two events as simultaneous, then for you, in your reference frame, they are simultaneous. Even if someone else moving differently calculates they shouldn't be because of light travel time.
Okay, the Alpha Centauri trip example really drives this home. It's 4 light years away. Suppose you invent a drive, maybe using that negative gravity idea, and you travel there in just 1 hour, according to your ship's clock.
Right. Your experience is 1 hour.
But an astronomer back on Earth watching your light trail, because light takes 4 years to get here from Alpha Centauri, they would observe your journey taking 4 years and 1 hour.
They see the light from your arrival 4 years after it happens.
So who is right?
Both, in their own reference frames. Fry's key takeaway is critical. The mathematics do not say that man cannot travel between the Earth and Alpha Centauri in less than 4 years. They say only that no observer on Earth can ever see him do it.
That completely flips our usual thinking about cosmic speed limits. It's about the observer's perspective, not necessarily an absolute barrier to the traveler's experience. Mind-bending stuff.
It really makes you question what's real versus what's observed. And from there, Fry takes us on the ultimate journey out into intergalactic space to see how new galaxies might form.
And step 1 is realizing there's no such thing as truly empty space.
Right. Even the deepest void has particles. Millions per cubic inch, he claims. Very diffuse, but there.
And these particles feel the pull from each other, but also the push from those distant massive galaxies, exerting that negative repulsive gravity.
Exactly. So over immense timescales, millions of years, these particles slowly drift towards regions of null balance between the repelling galaxies, pulled together by their own subtle mutual attraction. That's the seed of a new galaxy.
And it starts spinning.
Usually, yeah. Because the center of the push from surrounding galaxies and the center of the pull from the condensing particles themselves aren't perfectly aligned. This slight offset creates a torque, an angular velocity. So the cloud spirals inwards as it condenses, flattening into a disk shape. Starts as a dark nebula, invisible from Earth, just a vast cloud of gas and dust.
And within that giant cloud,
Local clumps form. Areas that happen to be a bit denser become gravitational centers, pulling in more material, forming individual droplets. These become stars.
how do they ignite?
As the particles fall towards the center of these protostars, their kinetic energy gets converted into heat through collisions. It gets hotter and hotter, denser and denser, until eventually it starts glowing. It emits visible light. The star has been born.
And these new stars are mostly hydrogen.
Primarily, yes. Because hydrogen is the lightest element, it's the most likely to escape the gravity of older stars and drift out into intergalactic space to become part of these new clouds.
Okay, take us inside one of these newborn stars. What's powering it? Fusion, right?
Right. Fry describes layers, an outer corona, super hot, trillions of degrees maybe, where incoming particles collide violently. Below that, the photosphere, denser but cooler, where most of the visible light comes from. And then the core. Unimaginable conditions. 20 millions of degrees, pressure in billions of pounds per square inch, density 10 times that of solid steel. Atoms are stripped bare, just nuclei flying around.
And those nuclei smash together.
They collide with enough force to fuse. When lighter nuclei, up to iron-silver, roughly fuse, a tiny fraction of their mass is converted directly into energy, a tremendous burst of radiant energy, mostly heat and light, following Yves Southrat. This energy pushes outwards, balancing the inward crush of gravity, and keeps the star shining.
Constantly replenishing the energy being radiated away.
Exactly. And the star evolves over billions of years, fusing hydrogen to helium, then maybe heavier elements, changing color from blue-white towards red, maybe ending in a nova or other events, depending on its mass and fuel supply.
And planets, how do they fit in?
Well, that stellar condensation process isn't always perfectly symmetrical. Maybe 1 in 4 or 5 times Phi estimates. There are secondary swirls, smaller eddies that condense separately but are caught in orbit around the main star. These become planets.
And they end up with heavier elements than the star.
Generally, yes, because during formation, the lighter gases like hydrogen and helium, being faster moving at any given temperature, are more likely to escape the weaker gravity of a smaller protoplanet. The heavier elements tend to stick around.
Which is good for us, I guess. It leads to rocky planets.
Indeed. And as these planets cool, form a crust, maybe get water, conditions can become right for complex chemistry. The formation of amino acids, the starting point of life.
Life. He thinks it's common.
Statistically, given the sheer number of stars and potential planets, he argues it's a virtual certainty on at least a few hundred or perhaps a few thousand planets just within our own galaxy. The ingredients and conditions should arise repeatedly.
Wow. And he ends with this idea about intelligent life spreading.
Yeah, a really thought-provoking image. That intelligent life, once it achieves space travel, might tend to radiate from the center of a galaxy outward toward the periphery, a slow expansion taking millions, maybe billions of years.
What an incredible arc. From redefining basic terms through the nullitron, atoms, heat, curved laws, negative gravity, all the way to galaxy formation and the potential spread of life. All built on this foundation of simple understanding.
It really shows the power of conceptual models.
Right.
Shifting your perspective, like embracing nonlinearity or relative observation, can unlock a whole new way of seeing how the universe fits together. It reveals a kind of elegance and interconnection you might miss if you're just focused on the math.
So as we kind of wrap up our own journey through Fry's ideas and head back mentally to our little planet Earth, way out here near the edge of the Milky Way, here's something to chew on. If intelligent life does tend to radiate outwards from the galactic center over cosmic time, what does that imply about civilizations that might be much closer to that origin point? What might they have figured out by now about manipulating gravity, space, and time in ways we're only just beginning to glimpse through ideas like these? Maybe the deepest dive isn't just looking out at the universe, but looking inward at how we frame it, how we understand its fundamental nature. Food for thought.